All right, so now that you know the different types of radioactive decay that are possible, let's learn how we could predict which type you would actually see given a specific isotope. So the different kinds that we talked about are alpha decay, beta decay, so that means an electron being emitted. We have positron emission. Positron is the same thing as an electron, but it's the opposite. So it has the same mass of 0, but weirdly it has a positive charge. We could also see something that we call electron capture. I'll talk about that more in a minute. Or we could see a gamma emission. A gamma ray is just photons of light, and so they don't have any mass and they don't have any charge. All right, so to determine which one might happen under any particular circumstance, the gamma ray, the only time I expect you to know that you would produce a gamma ray is if you have what we call a metastable nucleus. And a metastable nucleus is denoted by the isotope number. Let's say if it was this bromine one that we're talking about, it would be denoted by having a little m afterwards. What that means is you have part of your nucleus that is in a higher energy level than it would be most stable in. This is similar to how electrons can be promoted to higher energy levels and then fall back down. Nucleons in the nucleus can do a similar thing, and that emission, when it goes down to a more stable spot in the nucleus, will give a gamma ray. Pragmatically, you won't need to show me that there's a gamma emission unless you have a metastable nuclei with that M following its isotope number. The next easiest one to identify is the alpha particle. The alpha particle, whoops, I forgot to put the 4 and the 2 there. Okay, so the alpha particle, you'll see this when the atomic number is greater than 83. When that atomic number is greater than 83, the nucleus is too large to be stable. That strong nuclear force is extremely strong, but it only acts over very small distances. So if the size of the nucleus is greater than that distance, then the strong nuclear force isn't active over the whole length of the nucleus and it becomes very unstable. So you can start shedding the size of your nucleus by emitting alpha particles. So if your atomic number, so not the mass number, the mass number is written here, not that, but if the atomic number, so the actual number of protons, which you'll find on the periodic table, and is associated with which element it is, if that number is greater than 83, then you're most likely to see alpha decay. You may also see nuclear fission, but we're not going to predict those reactions for this class. All right, so next up on the list, if it's not one of those, it's going to be one of these 3, and that's a little bit harder to distinguish between these. So I'll talk about it for a couple of minutes as we go through these examples. But you can see a beta emission or an electron emission if something that we call your N to Z ratio is too big. And then you can see either a positron emission or an electron capture if this N to Z ratio is too small. Now I'm going to talk about what that means in just a second, so don't panic. All right, so let's look at our example that we have here. We want to predict the type of nuclear K that we would see in a bromine 75 atom, and we want to balance the reaction equation. So the first thing we'll do is we'll write our bromine with the 75 mass number up here. Next, you want to head on over to your periodic table and find the atomic number of bromine. The atomic number of bromine is just its number on the periodic table, right? That number tells you how many protons there are in the atom. So bromine has 35 protons. Our first question is it metastable? No, it's not metastable because there's no M written here. So not metastable. We won't see a gamma emission. Our next question is the atomic number greater than 83? No, because it's 35. So then we have to go over here and decide if our N to Z ratio is too big or our N to Z ratio is too small. So the N to Z ratio is talking about the neutron to the proton ratio. So N is standing for neutron and Z is standing for proton. If an atom doesn't have enough neutrons, it can convert a neutron into proton by splitting the neutron into a proton and an electron. So a neutron, I don't know if you knew, but surprise, a neutron is neutral because a neutron is a proton, which has a positive charge, and an electron, which has a negative charge, smashed together. So if there are too many neutrons in the atom, it can convert a neutron into a proton, and that will release an electron in that process. Now, the opposite can be true too, right? If you don't have enough neutrons, then you can convert a proton into a neutron by capturing an electron from the innermost shell, which is what we call the electron capture. Okay, so our question is, in bromine 75, do we have too many neutrons or do we have too few neutrons? I'm going to give you a really quick way to do this. This isn't the best way, so if you go on to be a nuclear chemist or a nuclear physicist, you'll learn more sophisticated methods, but this is a really good way to tell just as an introduction. If you go to your periodic table, you'll find not only the atomic number, but also the atomic mass. So the atomic mass of bromine is approximately 80. So we're going to compare that 80 to our mass number of this particular isotope. 80 is greater than 75, which means a stable isotope of bromine, which is what is naturally occurring, which is what the atomic mass is based off of, right? And a stable isotope of bromine has a mass of approximately 80, and ours has approximately a mass of 75. Both of them have 35 protons, but meaning a stable one has more neutrons than the one that we are talking about here. So that means our N to Z ratio is too small. It means that we don't have as many neutrons as we would see in a stable isotope of bromine. So that means that we're going to either see a positron emission or an electron capture. You will see an electron capture with bigger atoms, and then you'll be more likely to see the positron emission with small atoms. For the purpose of this class, if I can identify that the neutron to proton ratio is too small and write me either one of these equations, I'm happy. All right, so let's try and write an equation of either the positron emission or the electron capture. I'll actually write both so that you know how to do both of them. So with this, let's start with an electron capture. So that means that the bromine atom is actually going to take an electron from its innermost energy level of electrons. So that means the electron is actually part of the reactant side of the equation. So we've written our electron here, and then we just have to balance these so that they're the same. So on the top, we have a total mass of 75, meaning over here we need a total mass of 75. On the bottom, we have a total mass of 35 minus 1, which is 34. Then you just go over to your periodic table and you see which element is number 34, and you'll find that it's selenium. A bromine atom, by capturing an electron from its innermost shell, could turn itself into a selenium atom. Now the last thing you want to do is double check that this makes sense. So our N to Z ratio previously was 80 compared to the 75 that we had. So we should double check selenium. Now we have still 75, right? And we want to compare that to the atomic mass of selenium. If you look on your periodic table, the atomic mass is 75. All we're looking for here is to see if the ratio is better. This is better. Sometimes it can be the same, and that's still okay, but if it gets worse, you have done the wrong thing. So 75 is closer to 79 than 75 is to 80, so our ratio is better, which means this is a valid reaction expectation. So let's write the same equation because we said it could have been an electron capture or it could be a positron emission, just depending on how big the atom is. Instead of capturing an electron, it could have emitted a positron. Then all we have to do is balance this equation, right? So we have 75 up here, which means that the total mass of these two things need to be 75. Since that one's 0, this is also going to be 75. This is 35, so over here, we need to have a mass of 35. Since we already have one, that means this can only be 34. And you will look up on your periodic table which element is number 34, and you'll see it's selenium. So these equations look very, very similar. In both cases, we're getting a selenium 75 isotope, but the difference is in the second equation, a positron is emitted, whereas it's not emitted in the first version. It doesn't matter to me which one you choose as long as they balance. Now, the last thing you should do, as always, is double check. So atomic mass of this was 80, and that compared to 75, so that's how we knew it needed to be either an electron capture or a positron emission. And then now we have a molar mass of 79 for selenium compared to 75, and that is better. So we are good to go. Let's look at another example. In this case, we have proactinium 231. So remember, we could see alpha decay, we could see beta decay, we could see gamma emission. The first thing we do is to see if it has a little m. No, there's no m, so it's not going to be a gamma emission. Next, we look at the alpha. Alpha means that the atomic number is greater than 83. So at this point, y'all are going to want to learn the names of these elements so you can be familiar and know which symbols go with which ones, so you know where to look on the periodic tables. Proactinium 231, when you look at your periodic table, has an atomic number of 91. So that fits really well here. 91 is greater than 83, so we can expect to see alpha decay. So with alpha decay, we would first write, okay, we know it's going to be alpha decay, and then we can balance the rest of our equation. The total mass has to be 231. So that means 4 plus what is 231? 227. And then the total number of protons has to be 91. 2 plus 89 is equal to 91. Then look at your periodic table and see which element has 89 protons, and it is actinium. So this would be our balanced equation. Then we should always double check. The problem with this was that we had too many protons. 89 is closer to 83 than 91, so that is better. All right, let's try another one. Let's try bromine 82. Back to the bromine. All right, so we have bromine, isotope number or mass number 82. Then look at your periodic table. Bromine has an atomic number of 35. There's no M, so it's not gamma emission. 35 is not greater than 83, so this is not going to be an alpha decay, which means we have to decide about our N to Z ratio. To decide about the N to Z ratio, we look at the atomic mass of bromine on your periodic table, which is 80. And we want to compare that to the atomic mass that we were given for this particular isotope. In this case, the one we were given is greater than the one of the stable isotopes, which means our N to Z ratio is too large. We have too many neutrons. So if we have too many neutrons, this means you're going to see an electron being emitted from the reaction as it decays. So we have our beta emission. We have a beta particle or an electron, same thing, coming off of here. And then we just have to balance the equation. So our total mass needs to be 82. So 0 plus 82 is still 82. And our number of protons needs to be the same. So in this case, we've lost a proton through the beta particle. We've converted a proton into a neutron. And so our number of protons is now 36. Now this is the most common mistake that students make, is just forgetting this negative sign. And they're like, oh, 34 plus 1 is 35. But this is negative, so you need to have 36 minus 1 is 35. Then you can go to your periodic table and look and see which element corresponds to the one with 36 protons, and that is krypton. So this would be your balanced equation for this reaction. Okay, let's look at one last example. Technetium-99. This is used really often in medical diagnoses. So in this case, we have technetium-99. You can go to your periodic table and see that technetium is number 43. And here, finally, we see this M. And that M means we have metastable technetium. So if you see that M, what that means is that you will get the same exact nucleus back. So we still have a technetium-99, but that metastable version just means you'll have a gamma emitted from it.